So we're going to kick off the sessions, the afternoon sessions. My name's Thomas Vernon. I'll be the session coordinator for this afternoon. We first have 3 papers that will be presented. First one will be by Ievgen Kostiukevych, and actually myself, and 2 other co-authors on the paper. Then we will have a paper by Dennis Sandler on incremental live video processing. And then we'll have Huang Wang, who will present NVI. I will not run through bios. They're all available online, so there is no need to take some of the time from the speaker slots in order to maximize the time that they have for presenting and for Q&A. With no further ado, Ievgen, do you wish to kick off?
No, you haven't tried my bio, I insist.
Okay, so you want me to read your bio? No problem. Ievgen from DB. Go for it.
Hello. So, we're going to be talking about advanced timing and what we understand about advanced timing and why, and high performance timing for high performance media. There's a mouthful. You actually can do multiple modification in terms of our title. Just pick up your advanced high performance and then fill in the blanks, and you'll get another title, which actually kind of makes sense as well. Anyway, that to set up the scene and the atmosphere for the presentation, we're going to be talking about some pretty serious stuff, but we'll try to make it entertaining for you. And before we actually go into the meat and potatoes of the actual content, I want to answer the question that I heard the most times before actually getting on stage from multiple people already in this room, who asked, why do we need to talk about this? Because I thought we're moving into more software, more virtual, more asynchronous. And the answer is yes, you're absolutely right. There is absolutely no reason to do what we are talking about if you're doing software. If you are doing containers, if you are passing data between 2 different entities. But on the edge, if your software feeds a 16K virtual production wall that is driven by multiple rendering engines, this matters, and we will explain why. And this is where you absolutely need to be very tightly in sync. So, to explain a little bit what we understand by better pixels require better timing, through the power of my mental breakdown, we will now summon the voice into the room, and the voice will be belonging to Mr. Willem Vermoost, who unfortunately couldn't be here in person, but it is absolutely essential that we first do the introduction about why the work that we've done matters, and to quantify a little bit what was the motivation behind this work. So, Willem, if you hear us, could you please break it down for us?
As we dive into the evolution of picture quality, it's important to recognize that it's not just about increasing the number of pixels on the screen. It goes far beyond that, requiring improvements in various dimensions. We're talking about higher temporal resolution, a wider color gamut, and a greater contrast between the darkest and the brightest pixels. And of course, we can't forget about the audio enhancements that accompany these visual upgrades. The 2110 standard suite is designed to support this evolution, even reaching up to 16K resolution. To fully grasp the demands these advancements place on network infrastructure and timing precision, we need to revisit and understand the 2110 standard in depth.
Because put it like this
is used in 2110-25 document to illustrate measurement best practices. However, it also serves to highlight the requirements placed on a sender in a network environment. Let's consider sending, just for simplicity, a single image over the network. The data required to transmit just one image doesn't fit into a single IP packet. So the image has to be broken down and sent across multiple IP packets. Simply sending these packets all at once would overwhelm the network, causing packet loss and potentially even issues on the receiving end. The solution to this problem is packet pacing, which ensures packets are distributed in a controlled manner to avoid network congestion. This approach is an integral part of the 2110 suite, specifically addressed in -21, traffic shaping and delivery timing for video. Let's simplify things and leave out the concept of the gap. To avoid congestion, the packets representing a video frame are being evenly distributed over the duration of a frame. At the top of the illustration, you can see a theoretical representation of how a video frame arrives at the receiver. The individual IP packet that make up the frame are stored in a receiving buffer as they arrive. Then, at a precisely defined moment, the packet reach capital determines which packet is retrieved from the buffer to reconstruct a complete video frame. Thus, in an ideal situation, the packets are evenly distributed. Of course, a bit of tolerance is foreseen. In the standard, two tolerance levels are described, the narrow and the wide type. In other words, two levels of maximal jitter are described in the 2110 suite. This table might look complex at first, but it's actually quite straightforward. From top to bottom, we progress towards higher quality, or better pixels, starting with HD ready and moving through HD over UHD and finally to UHD2. We gradually increase the resolution. Along with that, we also raise the temporal resolution or frame rate from 50 Hz to 120 Hz and then up to 300 Hz for UHD and UHD2. For all but the last example, the chroma subsampling is kept to 4:2, and the color bit depth remains at 10. With these video formats defined, we can calculate how much data is needed to send a single frame over the network. Since one frame's worth of data doesn't fit into a single IP packet, we estimate the number of packets required, which can range from around 1,600 to as many as 140,000. To ensure smooth transmission, these packets must be evenly distributed over the duration of one video frame. Considering the even distribution, we can now determine the interval between each IP packet sent over the network. The time decreases from 12 microseconds down to 23 nanoseconds. This means the sender must place an IP packet on the wire every 23 nanoseconds. There is, of course, still a jitter budget available as in Cmax. Now, the timing difference here is by a factor of 1,000. So Thomas, can I assume the clock quality for HD could be lower than the required for UHD or UHD2? If I know my plant will be running in 1080p 50, does that mean I can opt for a cheaper clock?
Willem's always trying to get away with cheaper clocks.
Yeah.
So it's actually not about cheaper clock. It's more about what is the accuracy that is required for a given plant. So as Willem kindly explained, the differences in resolutions and the packet pacing that is associated with that implies that we need tighter and tighter timing for the higher resolutions. If you're building a 1080 plant, those requirements for the timing of the packet scheduling is less stringent than if you're trying to build a UHD2 plant, obviously. Which means that we should actually be able to tailor in one way or another, maybe through a class model, what are the requirements, what are the timing requirements for the individual.
But wait. So if we go back.
If we go back.
Yeah, okay. But then, look, the frame rate increases only slightly, right? Because if we're talking about the timestamping, the timestamp belongs to every packet of the same frame, and it's the same timestamp, right? So if we're doing 50 frames per second, that gives us something milliseconds per frame. Aren't we just good enough?
So you want to break this down into two ways. One is we're not talking about absolute time. We're talking about relative time first.
The UTC also.
Yeah, so you're not worried about, am I close enough for this? What I'm talking about here is I need to have a clock that is accurate enough to allow me to pace evenly, precisely, and schedule those packets at any given time for the temporal resolution I'm working at.
Right. So for UHD2, that's going to be 23 nanoseconds,
Exactly.
Which is quite tight.
It is quite tight, but not everyone needs that. So when Willem asks, can I get away with a cheaper clock? What he actually means is, can I get away with a lower accuracy depending on my requirements, but not relative to UTC traceable time, relative to my plant. As long as my whole plant is synchronized with one another to those requirements, I can get away with it.
So relative phase lock is what we're...
Absolute.
Not the UTC offset.
Correct. So other industries have actually worked on this problem for their own use cases. And I'm going to draw on the telecom industry, where the requirements for the radio access network are in the case of 5G. We have aggregated the frontal, and the radio units that are now in the field need also to have a coherent, aka phase-locked environment in which they can make sure that they aren't cross-talking between the different radio units. So they've come up with a model which has been defined not only for the 5G, but ultimately from the days when we went from analog to digital and then to carry Ethernet services, aka building telecom circuits over Ethernet. So the way they actually build this is they've come up with a whole series of recommendations. So they've actually broken down the problem into different parts of an overall system and say, again, we don't need the same requirements for all use cases, but we need different requirements for different use cases. So they have, just like in SMT with 2059, which is the PTP profile, or -2, which is the PTP profile, they've come up with 3 documents that actually cover their requirements. I'm going to go through the list of these as an illustration of how other industries have solved these kinds of problems, because the real problem we have, if you read 2059-2 today, it doesn't have accuracy requirements in there anymore. There was an accuracy requirement in the original. It was removed in the subsequent revision. And the same if we talk about what was built into the 2110 system. When the original design was done, we were talking about HD, not UHD2. So they have 8265.1, which ultimately is about how do we do frequency. On top of that, they have 2 different PTP profiles, because in their case, they've got environments where you have either a network that is full end-to-end, so full capability for timing, or partial capability for timing. So that's 8275.1 for full and 8275.2 for partial. Then the next series of documents they've actually worked on has to do really with how do we actually build the framework for the phase and the clocks. And this is extremely important, something that I would say doesn't exist today in the SENTI specifications. What are my actual requirements here? How do I put this together? How do I build a timing error budget that is end-to-end from the original clocks all the way to the endpoints, so I could actually paste packets at 23 nanoseconds should I need to. The same here with the 8272. So this is about the characteristics of the primary reference clock, aka what we call grandmasters. And they actually have this delineated in different classes of grandmasters. So here's the 8272.1, which covers enhanced primary reference clocks. Again, because the use cases have evolved over time, they have built specific requirements that match these use cases. And the last series of documents that allow you to build this overall system has to do with the 8273.2, sorry, the mouthful sometimes. So these are the characteristics of the different devices. We have boundary clocks and transparent clocks that are also in use in the SENTI 2059 model. They have built documents that tell you what are the timing characteristics for those given devices. Again, we need to quantify the expected performance of these devices, not just say, I need PTP. Yes, but what kind of PTP? How good? How accurate? How stable? What is my timing error budget? Again, here for transparent clocks. And last but not least, they also have a document in their terminology still called slave, which we call follower in SENTI, which has got to do with the endpoint itself. So it's very nice that we talk about the network and the time transfer across the network, but we need to go as far as the endpoint.
So they've specified the overall requirements. Then they've created a design guide for different network scenarios. And a characteristic requirement for every single network element, whether it's a boundary clock or a transparent clock.
Or an endpoint.
Or an endpoint.
Exactly. And also the grandmasters, the timing sources, the PRCs.
The actual source.
So we actually have the whole model, and we have the accuracy for the different parts of the model, which allows you to build out the different parts based on the requirements you have for your individual profile.
So let's say that my requirement from the Willems table, where does the 23 nanosecond fall in case of this framework? So let's say 23, what is that?
So in the way they deal with the problem, they've actually gone ahead and built what they call classes. So there's a so-called class A, B, C, and D, and each one of those have different timing requirements that are built into it. So again, we went through, say the example of mobile networks, we went through, 2G, 3G, 4G, 5G. Some of us are already working on 6G or beyond 5G or beyond 6G, depending on how you look at it. As part of that, you build in the requirements and you build in these different classes. So you could actually take a model like that and say, oh, look, to build my HD plant, I need class X. But if I'm building a UHD class, if I'm building a UHD plant, I need Y class. And if I'm building a UHD2 plant, I need Z class, as an example. So then you're able to quantify it and you're able to say, this is the timing error budget, aka the inaccuracy that I can live with for my packet pacing. How do I make sure that I can guarantee that? End to end, from all the components, from the reference clock all the way down to the endpoint. One caveat. When you get to the endpoint, you still need to make sure that the internals of the device are working as expected in order to make sure that you are scheduling those packets.
Right, because the 23 nanoseconds, it is our absolute point where the packet needs to hit the wire, right? Yeah. So this is our last possible error budget for the whole system, including all the processing in every single node.
Absolutely.
Okay.
So your time transfer has to be good enough to deliver better than 23 nanoseconds accuracy at the endpoint so that your packets are actually scheduled and coherent with all the other.
Better than, define better than.
Better than is, at this point in time, a subjective metric, but rule of thumb would be you need, 5-10 nanoseconds better than that because of the internals. And this exists in the telecom industry. So this is not science fiction.
Right. But if we're talking about the GNSS synchronization, isn't the maximum performance that you can get out of the GNSS receiver in the time server is roughly about 7 to 10 nanoseconds already?
Actually, it's worse than that. Even in the telecom specs, they are working on primary reference clocks that are up to, in the best case, around 50 to 70 nanoseconds off from UTC, from the traceable. But again, that's not the problem. We need to pace packets. We don't need absolute time. We need the whole system to be coherent and phase locked to the same source.
Right.
So as long as everybody's moving together within those 23 nanoseconds, life is good.
Okay. So again, we're talking about the relative phase lock of the system versus the absolute offset from the UTC, which doesn't matter for those individual packets.
For these applications. Okay. That's right. Got it? Okay. So then the question is, can we actually deliver this with today's infrastructure? So what we did is we took 11 switches off the shelf that exist in the industry and that are widely deployed. They shall remain nameless, so exhibit A to whichever one it is. And in the interest of time, we're not going to go through characterizing every one of them. They're in our paper, but we're going to explain how we actually measured this first of all, and then we're going to look at some of the results. Very simple setup. We have a device under test, aka the switch, that we're all running as boundary clocks in this case. And for those where we had the option of doing so, we try to make sure it was coherent, that within the same vendor they were running more or less the same software when we had that available for it, or at least some recent software when we were able to have that. We took a selection of different vendors, of different products that we know are used and deployed. And what we did is we used a device called a Paragon from a company called Calnex. There is no advertising in here. It's just a product that we used. And this allows you to do a number of measurements for compliance, specifically in the telecom space, but also they support the SMT profile. And the idea here was to say, we're going to use this as a common basis, as a device that has got an accuracy that is sub-nanosecond for these kinds of measurements, and we're going to run PTP through it, so it actually acts as the leader, then connected to the boundary clock, which becomes the follower, and then that port, then the next port becomes the leader, and then it's the follower. So we can measure the time error that is being generated by the device on the test.
Thomas, what's wrong with just reading the telemetry from the switch that typically gives you like the offset or whatever?
Ievgen, that's your view of the world, as in the stack, okay? The stack thinks it knows what it's doing, the PTP stack, but you need an external reference point. I can't measure myself against myself. I need to measure myself against an external reference.
The switch really knows what it knows.
What it thinks it knows.
Okay.
So how good is the time stamping engine? How stable is the oscillator? Am I running a fan against it? Is it stable in temperature environments that are changing? Did I spill my coffee over it? Whatever it may be. And in order to have a stable source to feed the test device, i.e. the Paragon Neo, we used a Grandmaster from a vendor called Meinberg, and we used the 10 megahertz output. So what we had is a stable timing source that was up and running consistently. We fed the 10 megahertz into the test device, which allowed us then to run a stable environment. All of this was running, so I'd say the timing reference and the test and measurement device, they were running for at least hours, if not days.
And that thing has an atomic oscillator in it. Kind of stable.
Yeah. But we still wanted to make sure that it was driven from a reliable frequency source. And every single device on the test was at least up and running for an hour. So we were able to, let's say, basic compensation temperature issues related to that. So we had more or less stable conditions. We ran 1 hour recordings of the test. So these are not long runs like 24, 48 hours. So it's just a snapshot of what you could expect from different devices. Shall I move to Exhibit A?
I think we can look at Exhibit A.
Okay.
Actually, I think we can involve our listeners here in discussion around Exhibit A.
Should they wish to join?
Yeah.
So,
Exhibit A.
Exhibit A. Exhibit A is a product that's been out on market for 6-7 years, I would say, roughly.
It's a relatively older, say mature platform.
Sure. Everything's tested at 10 gig, by the way, port speed. I didn't caveat that on the previous one. We didn't run extensive different port speeds. We decided to baseline everything at 10 gig. We have a peak-to-peak of about, 60, 72 nanos. So, in my eyes, it's pretty noisy. And we can actually see that we've got a mean of about 6 nanoseconds. So in terms of stability, not so good. Not so good. Good enough for some application.
Do you think it's good enough? Having heard all this, is this...
If you're building an HD plant.
Yeah.
Good enough?
Good enough?
They're saying yes.
Okay.
They're saying no? They're saying yes. Okay, good enough for HD, no question. The problem is you're building a timing chain. So if I have 10 of these, my timing error budget will always increase hop by hop. So it may or may not be good enough.
All right, because if I sequence, say, 3 of them, does this mean that this is the equal performance that we'll get in the end?
Non-linear.
Non-linear?
No, because I will have it additive at best to some extent, but each one will generate its own noise, which will go into the next one, so I have additional timing inaccuracies. So ultimately, I want to test the chain end to end.
So it's not only crap in, crap out.
It's crap in, crap out multiplied by something which...
Getting crap, yeah.
Exactly.
Okay.
So typical product out on the market, runs in many plants, running HD.
Exhibit B.
Exhibit B. So Exhibit B, look good. I mean, we scale all the graphs to be identical, but...
And this is also a platform that is out there.
Oh, yes.
Yeah, okay.
Absolutely. It looks good because you see a peak-to-peak of about, 4 nanos, roughly? You're like, wow, that's tight.
And so what is that in the middle?
Oh, you mean the little sudden jump and then jump again and then jump back and everything else?
Yeah.
That's some sort of compensation that's being done.
Why?
Good question. Did a fan turn on? Did the temperature in the room change? Did someone spill something on it? Was there a PLL in there which decided to go foobar for whatever reason? That's not my problem. My problem is that it's an instantaneous jump. There is no, smoothing of the error, neither at the start nor at the end. So that means your whole plant, or everything that's downstream from it,
Everything downstream.
Everything downstream is going to jump. Good, bad, ugly, depends what you're doing.
Throw some previous exhibits into it, and it's going to be fun.
Yeah.
Okay.
So then you could combine this and say, hey, I've got this guy. So this guy, he's like average, he's got 30 nanos of peak to peak. Not too bad. He's quite stable, 1.2, or 1.8, I should say, nanos. But if you really look at it, it's moving around. Now this is a 1 hour plot. So we don't know what it looks over a 24-hour cycle or 48 or whatever. Again, it's in a data center. Did suddenly the aircon come on again? As it happens in phases, on, off, and we're seeing this shift. Maybe, maybe not. Is it something else? Who knows? So this is just a snapshot of what you could expect. But depending on what is connected downstream from it, it might see other side effects, and it might be increasing. So if we build suddenly a chain with the 3 devices we've got here, out of the 11 that we've tested and are all in the paper, you would have some additive timing error that could be quite interesting. You could have some jumps due to what we saw in the previous exhibit. You could have some noise from the first one. And then you could have this one which looks nice, but something is shifting in there. So, you need to understand this and quantify it.
But the common knowledge tells us that if you get an expensive oscillator, you're good. And that is what probably we have in the exhibit B, right? Because it's very, very tight.
It's tight. Someone's written some good software, much like a good control loop. DPLL in there might be good, but still, the way that it's implemented.
The jump. Okay.
So this is why you always have to test your infrastructure and not read data sheets. You can read the data sheets, but you want to test it. So the point here we're trying to say is different products on the market provide different timing qualities. Those different timing qualities will impair or impact what your target is in terms of building 2110 systems for HD and beyond. And due to that and the packet scheduling requirements, we need to understand this, especially that there's a void in the current spec, because no accuracy requirements are defined as to how this should operate for packet pacing 2110 flows. Ievgen, I'll hand back to you.
Yeah, so the main message here is, as you may have noticed, we never said that Exhibit A was bad or Exhibit B was good. The answer always going to be, it depends, right? There are systems out there that are built with these products that run perfectly fine until they not. And there are systems out there that may be running better or at least more predictable, more stable. And it's not just the lack of requirements towards the end error budget, but it's also a point of understanding on how you design those solutions and what is your principles and guiding lights in terms of picking a suitable switching platforms, network elements, but also your time servers. Because if you invest in a very expensive cesium-based clock in the heart of your data center and then push it through one of those exhibits B, well, you've just wasted a few dozens of thousands of whatever money you're dealing with on that cesium clock that is going to be completely wasted with the performance of your switching elements. Again, and also it is just not the not just the point of picking the expensive oscillator in your switch platform, because your vendor will say, well, we have, rubidium oscillators in our switches. Great, but also, are you doing good control loop in front of that, like with Exhibit B, that sudden shift? God knows how your endpoints will react to that shift when the whole system shifts. And we actually saw that in one of the broadcasters when the system just suddenly jumped into the future from the timing perspective and caused complete havoc and chaos downstream. So, is there a product to sell? No. Is there I don't know, a solution that we can offer? No, not yet. So this is one of your rare non-marketing driven presentations that basically says, let's just think about it. Maybe there are some considerations that we're not paying enough attention to when we design our systems or when we talk with our vendors. None of the vendors that we've tested and none of the platforms have this stuff kind of published or at least talked about, except for one particular vendor. But they're in a different business. We just use them as one of the benchmarks. And also they're not in those screenshots, so you will not be able to guess which one. Read our paper. We got much deeper into the details about the reasoning behind and somewhat a call for action, a call for conversation. And if you have something to say, join that conversation, or if you have any questions, we're happy to answer. Thank you.
John? I don't know if there's a mic.
Hello?
Now I'm getting worried.
Can you hear me?
Yes.
Yes. Thomas, Ievgen, thank you. It's an excellent presentation. And as usual, it really makes me think. Anytime I hear Thomas's presentation, I'm always walking away, scratching my head. I'm John Snow, Cobalt Digital, and maybe more pertinent to this question, chair of the 2059 drafting group. Is there anything SMPTE standards, whether it's 2059 or 2110, should be looking at to help this situation?
Short answer is yes. The short answer is there is a gap. We've documented the gap, and we would love to see SC pick it up and work on it to address the concerns that we've raised in the paper. Any other questions? We're around for the rest of the afternoon for those who wish to have one-to-ones. Okay, that's it from us. Thank you.